Here in the Hermite's polynomial 2, we are going to follow the same method what we have followed earlier in case of legendary polynomial or legendary special function. There we are supposed to first, now we are not going to discuss its background, from where this Hermite polynomial comes and all that. Actually, that is when we solve this Hermite differential equation in the spherical polar coordinate system, we come across this Hermite differential equation, and this equation plays a very vital role or important role in the study of the simple harmonic oscillator in case of in the quantum mechanics. So we are not going to discuss that particular background, but how Hermite polynomials are defined using certain generating function. Yesterday in the earlier lecture we have seen how generating function gives rise to this type of polynomials, that we are going to discuss. At the same time, there is one more method that is called as a Rodrigues formula. For this polynomial also there exists one Rodrigues formula. We can use that formula and get first few Hermite polynomials one by one, and apart from that there are certain properties associated with that Hermite polynomial, that is also we are going to discuss one by one. Okay, so let's begin with this first one. Hermite's polynomial can be determined. Hermite's polynomials can be obtained from the generating function g of, here also the generating function is of the two variables x and t. Okay, when it is expanded around t is equal to 0, when it is expanded around t is equal to 0. Okay, then the Hermite's polynomial, actually it is Hermite, Hermites, Hermite's polynomial. Okay, now symbol used here, it is hn of x. Okay, n is the order, x is the variable, h is the symbol for Hermite polynomial or Hermite function. Occur as coefficients of t raised to n upon n factorial. This is additional part here, t raised to n upon n factorial in power series. Okay, remember in the earlier case, in legendary case, we have also written same statement there, that is g of xt is the generating function, which is given by 1 minus twice xt plus t square raised to minus half. If it is expanded around t is equal to 0, we get legendary polynomials Pn of x as coefficient, this particular occur as a coefficient as of t raised to n in the power series. So same statement is there here also, we are using the same statement. Now the GF, generating function for Hermite polynomial is, okay, if it is exactly of the same form, this is given by g of xt. You have to remember this, g of xt is equal to e raised to twice xt minus t square. This is the generating function, and as it is expanded around t is equal to 0, we get here, this is n equal to 0 to infinity. This coefficient is hn of x. These are the Hermite's polynomial, and this is multiplied by t raised to n upon n factorial. Okay, now call this to be equation 1. This is our definition of Hermite polynomial using the generating function e is raised to twice xt minus t square, where x and t are two different variables. Okay, now consider this GF, generating function. Consider the generating function as I am given the generating function g of xt is equal to e raised to twice xt minus t square. Can anyone tell me the expansion? Expansion e raised to x is given to be 1 plus x plus x square upon 2 actually it is 0 factorial divided by 1 factorial plus 2 factorial x cube upon 3 factorial plus x raised to 4th upon 4 factorial and so on. This is an infinite series. Exponential e raised to x is an infinite series which is given by this formula. So here also I am taking this to be an x. So I can use this expansion here. 1 plus first bracket is twice xt minus t square raised to 1 upon 1 factorial. Second bracket is 1 upon 2 factorial into twice xt minus t square square of the bracket plus 1 upon 3 factorial into twice xt minus t square raised to 3 and so on, higher order terms. Now just expand these first two. There is no need to go for these terms. I can expand this. So 1 plus, now this gives me 4x square t square minus 4x t cube, product in between of this, and plus t raised to 4th. This is first expansion. Plus 1 upon 2 factorial in the denominator, and this is now sorry, we have, this is not needed here. It is okay. I'll scratch this. Don't take this statement. I'll expand this. 1 plus first term is twice xt minus t square, okay, from this first, and here it is 1 upon 2 factorial into 4x square t square minus 4x t cube plus t raised to 4 and plus so on, higher order terms. Now what we have to do, take terms of t together, t raised to 0, t raised to 1, t raised to 2, 2 raised to 3, etc. So here t raised to 1, t raised to 2, here t raised to 2 and t raised to 3. So next this term is to be taken from this second bracket here while taking this t square term together. So using this, if I go for this, I'll get another equation as first equation is, first term will be 1, then second term is now obtained to be twice x into this t, okay, divide by 1 factorial. It is there, it is already there in 1 factorial. 0 factorial is here, we are not writing that. So this is my first term, and plus I'll get 2 into, now this is t square here, and this is 4 upon 2 factorial, okay, or you can write this 2 factorial there, doesn't matter. You can write this is here, I can write this is t square upon 2 factorial as it is. Now t square is taken common out of this, so here it is 1 t square and there is 4x square is there, and out of that 2 is taken outside, and if it is taken this way, when one gets this particular equation as 2 into bracket twice x square minus 1 into t square upon 2 factorial and so on. So this expansion you can check, you can go for actual solving this. So how to get terms t raised to 0 together, t raised to 1 together, t raised to 2 together, t raised to 3 together, likewise, and then you can get this type of particular series there. Okay, that is what my equation number 2. This is my equation number 2. Okay, and now as per our earlier definition, we have this g of xt is equal to summation over n equal to 0 to infinity hn of x into t raised to n upon n factorial. So if it is expanded for all values of n, I'll get first will be h0x into t raised to 0 upon 0 factorial. Second term is h1 of x into t raised to 1 upon 1 factorial plus h2 of x into t raised to 2 upon 2 factorial and so on. This is my equation 3. So here t raised to 0, t raised to 0, t raised to 1, t raised to 1, t raised to 2, t raised to 2. Likewise, we can compare this. So comparing equation 2 and equation 3. Okay, we will get very easily, we will get what are these. Now we will get first Hermite polynomial of order 0 of x is equal to simply 1. Then h1x order 1, 0th order is 1, first order is this particular term, so it is twice x. Then similarly comparing third term, that is h3 of x, this coefficient will be, as it is given here, 2 into 2x square minus 1. So there is 2 into twice x square minus 1. So expanding this, I'll get 4x square minus 2. Similarly, one will get h4x, sorry, this is h2x, h3 of x. Third polynomial, if it is obtained, it will be 8x cube minus 12x, and so on. So all these are first few Hermite polynomials. These are first few Hermite polynomials. So exactly same polynomials we obtained in the chapter number 3 for TYDSA I am talking. So same polynomials we have obtained in case of the series solution method, from the infinite series, how we received or how we obtained these polynomials by truncating this, putting certain conditions over that, and these were the polynomials. h0x is equal to 1, h1 of x is equal to 2x, h2 of x is equal to 4x square minus 2, h3 of x is equal to 8x cube minus 12x. So this is the method we can obtain polynomials or Hermite polynomials from the generating function. Now the second method, Rodrigues formula. Rodrigues formula for this. So as exactly in the similar way what we did in case of legendary polynomials, same thing can be done here. So Rodrigues formula in this case is given to be, okay, so the Rodrigues formula for R capital, Rodrigues formula for Hermite polynomial is, okay, yesterday we have written that Rodrigues formula for legendary polynomial. Here for this polynomial, this formula given is, again it's very simple. Hn of x can be obtained by taking this calculation. It is minus 1 raised to n, even and odd, that will be decided here, e raised to x square into d raised to n upon dx raised to n of e raised to minus x square. So try to understand this. This is e raised to x square into d raised to n upon dx raised to n into e raised to minus x square, and this is minus 1 raised to n. That is the expression of the formula which is called as the Rodrigues formula for the Hermite polynomial. Okay, now take n is equal to 0. Now if I put n is equal to 0, this will become h0 of x is equal to, now minus 1 raised to 0, e raised to x square, then this is d raised to 0 upon dx raised to 0 into e raised to minus x square. So here this, it becomes simply 1, because anything raised to 0 is taken to be 1, and minus 1 raised to 0 is also 1. So this is simply e raised to plus x square into e raised to minus x square. So this exponent cancels each other and will get simply 1, and therefore from this calculation I got first Hermite polynomial h0x is simply 1. Likewise calculate second, that is n equal to 1. N is equal to 1, I should get, this is h1 of x is equal to, now write that in the Rodrigues formula, minus 1 raised to 1, that is negative, then e raised to x square as it is. Now this is d by dx, d raised to 1 upon dx raised to 1, and multiplied by e raised to minus x square. So get differential of this, we'll get minus 1 raised to 1 is minus 1, this will be there, e raised to x square is there. Now this e raised to minus x square will come out, and differential of this will be minus twice x. Differential of this minus x square is minus twice x. So this e raised to x square and e raised to x square cancels, and minus 1 and minus 2, this gives me twice x, and therefore my first legendary polynomial or legendary polynomial of degree n equal to 1, that is simply equal to twice x. So that is what we have already calculated, we know that, and this is the second. So that is what second member of this Hermite polynomial is calculated there, h1 of x, it is equal to twice x. Similarly calculate h2x, now n is equal to 2. Okay, this only, h2x is equal to, now it is minus 1 raised to 2 into e raised to x square d square upon dx square of e raised to minus x square. So can you write this as minus 1 raised to 2 is 1, no need to write this here. So e raised to x square, I can write this as d by dx of, again in the bracket, d by dx of e raised to minus x square. So simplifying this, I'll get e raised to x square as it is, then d by dx of, so first bracket, this differential gives me minus 2x into e raised to minus x square. Differential of this differential with respect to dx, I'll get minus 2x into e raised to minus x square, and further we have to get this is e raised to plus x square into, now d by dx, there are two functions, so it is d by dx of minus 2x into e raised to minus x square will remain as it is, and second time it is plus, now this minus 2x will be as it is, and differential of this d by dx of e raised to minus x square. Solve this, so e raised to plus x square into, this is minus 2 here, this differential, into e raised to minus x square, then here it is minus 2x as it is, and differential of this again differential of this is again minus 2x into e raised to minus x square, and this e raised to x square is multiplied there. Okay, actually it should be like this. Solving this further, it is e raised to minus x square and e raised to plus x square is 1, so it is simply minus 2 there in the first term, then minus 2 into minus 2 is minus 4x square, so it is plus 4x square, and this is e raised to plus x square multiplied by e raised to minus x square, so this again cancels and we get a simple term 4x square minus 2. So this is my h2 of x. So that is how we have obtained all these three members of Hermite polynomial using this Roderick formula. Okay, from the examination point of view, or please remember, this is sometimes asked, you are not given Roderick's formula. Roderick's formula is to be remembered for this type of Hermite polynomial. This is as it is given, so this is given to be minus 1 raised to n e raised to x square into d raised to n upon dx raised to m into e raised to minus x square. This is the Roderick's formula. Put values of n equal to 0, 1, 2, etc. You will get each and every member of this particular Hermite polynomial as what we have done here. So there it requires a knowledge of differentiation, knowledge of mathematics, and that will lead you to the following polynomials as we have shown there. Okay, so let me make a chart here, small chart. That is how I got, just a minute, let me make a small chart. We have to plot them. We got this h0x is equal to simply 1, h1 of x is equal to, just now we have obtained, it is twice x, then h2x as we have just now obtained is 4x square minus 2, and h3x, if I know, we have already written it, it is 8x cube minus 12x. Okay, actually we are not going to plot this, but we can plot remaining. Now let us plot the first few Hermite polynomial, first few Hermite's polynomial. Just try to plot this. If you want to plot, you can plot or not. So this is a very simple function. this is my x, and here this should go down. Now this is 0, then this is 2, 4, 6, etc. This is 2, 4, 6, 8 and so on, and here it is minus 2, minus 4 and so on. So this is my hn of x, this is minus hn of x. Now see, first equation, first was polynomial of all values of x. Okay, you can take left hand side too, you can take right hand side too, doesn't matter, but for all values of x right from 0 to infinity, this function gives me only this line. So this is first polynomial, if it is plotted, which is parallel to x axis. So this is my h0 of x. So its value is 1 for all values of x, doesn't matter. Then here h1x, if I go for this, whatever x, h1x is double of that. So when I take this to be 0, x to be 0, h1x is also 0. But when I take this x to be equal to 1, suppose this is 1, 2, 3, 4, 5 and so on. So if I take 1, I'll get this is to be twice x. So this point will be obtained to be here. Then I take 2, it will come to be 4 here. When I take 3, then this will be 6 here. So connect all these points, you will get this is the polynomial of order n equal to 1. So this is my h1x. We are plotting this. It's very simple to plot because x, whatever value of x, this h1x will be twice of that. So it is twice x. So you will get a line passing having a slope to be shown by that particular curve there. Then put values of x equal to 0 here. When I put value of the h2x, or we do this calculation, 4x square minus 2. Now this is my h2x. Put x is equal to 0. When I put x equal to 0, h2 of x will be equal to, this will be 0 minus 2, it is minus 2. So I'll get this point. Put x is equal to 1. So x is equal to 1 is now h2 of x will be equal to 4 into 1 minus 2. So that will be simply 2. So when I put 1, I'll get 2 here. Again same point. Then put x is equal to x equal to 2. So h2 of x here in this case is h2 of 2 is equal to 4 into 4. It is 4x square minus 2. So it is 16 minus 2 is 14. So this number will be very large somewhere here. You can not show here. And if it is joined, one will get this curve is passing here and this curve reaches very high. So this is my h2x and so on. So I got h0x, h1x, h2x, etc. that can be plotted here as shown by this diagram. Of course, again my diagram is not to the scale, so you should look any standard reference books or a textbook. You will get a nice picture of this Hermite's polynomial very easily. Or at the end of this lecture, I can show some of the diagrams from the internet that will give you how this particular polynomials look like. So that is what we have done for positive part of x. So negative part of x also we can plot, or we can go for here. We will get the curves on the left hand sides too if you want from this. So here we have understood this process, how to generate or how to obtain this Hermite polynomial from the generating function, as well as how to obtain it from this Rodrigues formula. Both of the methods have been seen, and at the same time we have seen how it can be plotted on the graph as shown by these equations. h0 x is equal to 1, h1 f x is equal to twice x, h2 of x is equal to 4x square minus 2. Similarly, h3 of x is equal to 8x cube minus 12x. Put values of x from minus infinity to plus infinity and plot this curve. You can plot this curve very easily as shown by this. On the graph, plotting is much easier as compared to here what we have done here. That is not to the scale, but if this type of diagram is plotted to the scale, we get a very nice diagram of this Hermite polynomials too. Okay, this is what we have finished this. Now let's go to understand some important properties. So next title, properties of Hermite polynomial. properties of Hermite polynomial. Exactly similar. Whatever properties we have discussed in case of Legendre, same properties also can be shown here. Okay, first one. Here it is hn of 0, x value is equal to 0, is equal to 0 when n is odd. That index or power is odd, then I'll get hn of 0 is equal to 0, and hn of 0 is equal to minus 1 raised to n by 2 into n factorial divided by n by 2 factorial when n is even. You have to show from this generating function itself, we can show that hn of 0. So now take any order of Hermite polynomial for all values of x. So h1 of 0, h2 of 0, h3 of 0, h4 of 0, whatever. So out of that, for odd value of n, we will get this h1 of 0, h3 of 0, h5 of 0, etc. These all odd Hermite polynomials will be equal to 0 for value of x equal to 0. Whereas when I put even polynomials, in that case this is given by if I am going for fourth polynomial h4 0, then it will be minus 1 raised to 4 upon 2 into 4 factorial divided by 4 by 2 factorial. This number will be calculated. How, whether it is correct or not, that can be done as follows. Now let's go for its proof. Okay, so its proof, we have to go for, consider the generating function. Generating function g of xt is equal to minus 1 raised to n into e raised to x square d raised to n upon dx raised to n into e raised to minus x square. Just a minute. Ganesham sir, hello. मी लेक्चर मध्ये मी एक अर्ध्या तासाने फोन करू का? मी करतो. So this is what the generating function we have been given. No, sorry, we have written this. This is not correct. What is this? It is the Rodriguez formula. I am discarding. So I have written Rodriguez formula. Generating function is different. Generating function is e raised to twice xt minus t square. That is generating function. Now put value of x equal to 0. At x is equal to 0, we get g of 0t is equal to, this is now e raised to 2 into 0 multiplied by t minus t square will be simply e raised to minus t square. Now we can use this expansion of e raised to x. It is 1 plus x, so it becomes minus t square plus t raised to 4th upon 4 factorial, sorry 2 factorial, 0 factorial, 1 factorial, 2 factorial, then minus t raised to 6 upon 3 factorial plus t raised to 8 upon 4 factorial, and likewise plus minus etc. Nth term will be given as minus 1 raised to n into t raised to twice n, nth term I am talking, upon n divided by 2 factorial plus higher order terms. So this is nth term, first term, second term, third, fourth, fifth, sixth, etc. So for the 0th term it is 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, and alternate terms are plus and minus. So first term is plus, second is minus, third is plus, fourth is minus. So 0, 2, 4, 6, etc. These terms are even. Here whatever n I am taking, this power is twice n. First term, 0th term, t raised to 0. Term 1, n equal to 1, this power is square, n equal to 2, power is 4. Likewise, this is t raised to twice n. So how to write nth term in that particular series, that also can be understood from first previous few members. So I can see here, this is now second term, so 4 factorial, so 4 upon 2 factorial is 2 factorial, 6 upon 2 factorial means 3 factorial. So I'll get this. So I can write this nth term is shown this particular way. Okay, so one can write this as I can make a certain change here. Now let's rewrite this as in the following manner: 1 minus 2 factorial into 1 upon 1 factorial, not I, this is factorial, okay, into t square upon 2 factorial. Now I have not done anything change, काही मी बदल केलेला नाहीये. हा 1 factorial तिथलाच आहे पहिलाच, याच्यातला इथलं ह्याच्यामधला t square मधला. There was 1 factorial was there, t square was there. I have added 2 factorial here in the numerator and divided it by 2 factorial in the denominator. So I have not done any change there. Similarly, for the next term I can write 4 factorial divided by 2 factorial into t raised to 4th upon 4 factorial. It is there, t raised 2 factorial was there, t raised to 4 was there. This is to 4 factorial divided by 4 factorial, so divide and multiplied by that same. Next term now plus minus plus, it will be now minus, so it is 6 factorial divided by 3 factorial into t raised to 6 divided by 6 factorial. Likewise, so same thing can be done here. For the next terms I can write this as minus 1 raised to n upon n factorial, then this is 2n factorial. Okay, like it is 4 factorial झाला आहे, 6 factorial झाला आहे. This is n factorial and this is 2n factorial, like that, n factorial and twice n factorial multiplied by t raised to twice n upon, to cancel this I'll have write this to be 2n factorial and plus like this. So this is nth term. Try to understand how we do write nth term using this. And remember, as per our knowledge, we have g of 0t is equal to summation over n equal to 0 to infinity. Now this is hn of x into t raised to n upon n factorial. So expanding this, I'll get this to be h0 of 0 plus h1 of 0 into t upon 1 factorial minus, now it is second term, okay, it's plus, doesn't matter. Then it is we are expanding this, so it is h2 of 0 into t square upon 2 factorial plus h3 of 0 into t raised to 3 upon h raised to t square upon 2 factorial t raised to 4 upon 4 factorial, and likewise I'll get nth term here also, which will be given by hn of 0 t raised to n upon n factorial. This is nth term, and plus twice nth term will be as given by h2n, twice nth term will be of 0 into t raised to twice n upon 2n factorial. Okay, जरी थोडंसं नंतर बारकाईने बघा प्रत्येक टर्म कशी त्याच्यात येते. So I can call this to be equation 1 here and this to be equation 2, and just compare this. So comparing equation 1 and 2. Comparing equation 1 and 2, one will get very easily. Okay, so odd, all odd terms. So here it is h0 0 t raised to 0 upon 0 factorial, h1 0 into t raised to 1 upon 1 factorial. Here actually, and comparing this was negative. Here this is now positive. Again this is negative. Then this is positive. Likewise, in that case we will get, that is when we get hn of 0 is equal to 0 for odd n. Okay, odd n is not existing there. Compare here. You are not getting term for t raised to 3, t raised to 1, t raised to 5, t raised to 7, etc. That terms are not obtained in this equation number 1. Therefore, I can easily write, comparing these two, hn of 0 if n is odd is simply equal to 0. There is no such coefficient for t raised to n, which is n is odd power. Odd power, there is no coefficient. Therefore, all hn of 0 is equal to 0. That is my first part. And second, h2n of 0 is equal to, that is what we have written in there. It is minus 1 raised to n into twice n factorial divided by n factorial for even n. For even n. Okay, and replace n by 2. Here also we are making a small change. Replace n by 2. Okay, just to make this to be hn. I'll get hn of 0 is equal to, see this is h2n we have taken from here, this equation, and therefore replacing n by 2, I'll get this is hn of 0 is equal to, now this is minus 1 raised to n by 2, replacing this n by 2, then twice n factorial, so replacing n by 2 will get 2 will get cancelled, so we'll get n factorial divided by n by 2 factorial. Okay, and this is my result, second result 2. So again this is result 1, and sorry, this is result 1 and this is the result 2. So here we have proved one such property of this Hermite polynomial of nth order for x is equal to 0. This gives me this type of understanding, or given by this example. This is first property. Second, number 2. Second is, show that hn plus 1 of x is equal to twice x into hn of x minus twice n hn minus 1 of x. So this is also a recurrence relation. This is also a recurrence relation. Now we have to get this recurrence relation again using exactly similar method what we did earlier in case of that legendary polynomials. We have done all these things. So proof from the examination point of view, this is IMP from the Hermite polynomial. So consider the generating function g of xt is equal to e raised to twice xt minus t square. That is given by expansion n equal to 0 to infinity hn of x into t raised to n upon n factorial. This I know. Okay, now here is not dash, means we have to differentiate this with the second variable t. So differentiating with t, variable t. So let's see, differential of this will be here it is differential of twice xt with respect to t is twice x, differential of t square is minus twice t, and since this is expansion term, so it will remain as it is twice xt minus t square of the left hand side, and here is function of t is this. So I'll get summation over n equal to 0 to infinity. This is n times hn of x into t raised to n minus 1 upon n factorial. This differential with respect to t. Okay, now you can replace this from this earlier you can 1. this is 2. I can use equation 1 in equation 2 here. Therefore, I can write this is in the bracket twice x minus 2t. This can be written as summation over n equal to 0 to infinity. This is hn of x into t raised to n upon n factorial is equal to summation over n equal to 0 to infinity. This is n times hn of x into t raised to n minus 1 upon n factorial. I have done nothing. Only the second term I have replaced by second on the left hand side. This e raised to twice xt minus t square has been replaced by that. Now simplify this. There are two terms on the left hand side now, 2 into x and this. So first term is twice x summation over n equal to 0 to infinity. This is now hn of x into t raised to n upon n factorial minus 2 outside of this, n equal to 0 to infinity. Take this t inside and therefore it becomes hn of x into t raised to n plus 1 upon n factorial. Simplification. And that is equal to summation over n equal to 0 to infinity n times hn of x into t raised to n minus 1 upon n factorial. Now what we have to do? I have to look that each power in each term will be t raised to n upon n factorial or t raised to n. So equating the power of t raised to n. So for that I have to make a change in the second term on the left hand side as well as first term on the right hand side. So in the second term I have to replace n by n minus 1, then I'll get t raised to n. In the last term on the right hand side I have to replace n by n plus 1, then I'll get t raised to n. So accordingly making these changes. So right here comparing coefficients of t raised to n. Comparing coefficients of t raised to n. शरण्या आवाज येतो का माझा? हॅलो?
हो सर येतोय.
हा, नाहीतर मी आपलं शिकवायचो एकटाच आणि तुम्ही सगळे बसलाय निवांत तिकडे, असं नको व्हायला.
येतोय.
ओके. आर यू रायटिंग? लिहिताय ना तुम्ही?
येस सर.
ओके. कोएफिशिएंट ऑफ t raised to n on both sides of above equation. I am just looking here. Now we can remove this summation over n equal to 0 to infinity. If this is removed, I'll get this to be simply twice x into hn of x upon n factorial, left hand side, minus here I have to replace this n by n minus 1. So this is hn minus 1, n minus 1 factorial, and here it is t raised to n. So that was, I write here to be 2 hn minus 1 of x divided by n minus 1 factorial is equal to, here I have to replace this n by n plus 1. So here it becomes n plus 1 outside of this, then hn plus 1 of x into t raised to n, that is not needed, divided by n plus 1 factorial. Now I am making small change there. याच्यामध्ये आणखी एक छोटासा चेंज आपण करतो. So let's write this to be twice x into hn of x upon n factorial. Then I am writing here minus 2. Now n factorial divided by, this is n factorial into n minus 1 factorial. See what I have done. I have multiplied numerator as well as denominator by n factorial, and this is hn minus 1 of x. This and this has been added there. Now 5 factorial into 4 factorial is 5 factorial. So कुठला n factorial into n minus 1 factorial is n factorial. So is equal to n plus 1, and here this term can be written as hn plus 1 of x, and this can be written as n factorial into n plus 1. This term n plus 1 factorial, that means 5 factorial can be written as 5 into 4 factorial. Okay, this way I have written n plus 1 factorial is equal to n plus 1 into n factorial. So that is what here. Now we look here, there appears n1 n factorial here in first term, n factorial appears here also, n factorial appears here also, that can be cancelled. Then this one of this n plus 1 and here n plus 1, that can be cancelled, and therefore I'll get this equation as, so what cancels and what remains is twice x into hn of x minus, sorry this term I have should not written this to be n factorial, this should have been, okay, now make a correction here. This correction is, should not be this factorial here, should be only n. Okay, I'll write once again. So this is simply n upon n. Then this entire thing becomes n factorial. हे सगळं याच्यानंतर किंवा मी पुन्हा एकदा लिहितो, divide by n factorial minus twice n into h n minus 1 of x. This is n factorial into n minus 1, sorry, n into n minus 1 factorial is simply n factorial again. 5 into 4 factorial is 5, like this, is equal to this, and this gets cancelled, and I'll get h n plus 1 of x divide by n factorial. So here, here and here, in both of all these three terms there appears n factorial. So cancelling this, will get final expression as, therefore twice x into h n of x minus twice n into h n minus 1 of x is equal to, I'll get this is h n plus 1 of x. Okay, and this is called as a recurrence relation, because knowing h0 and h1 one can find out h2, knowing h1 and h2 one can find out h3, knowing h2 and h3 one can find out h4. So thereby all Hermite polynomials can be obtained from this. So write one statement here. This is the three-term recurrence relation. Three terms recurrence relation. Because knowing h0x and h1x, we can obtain h2x. Okay, this is like h0, this is h1, this is h2, so like that. So knowing h0x and h1x, we can find out h2x. Knowing h1x and h2x, we can obtain h3x, and so on. Higher order terms also can be obtained, and that's why all Hermite polynomials of degree n equal to 2, 3, 4, 5, 6 etc. can be obtained, provided we have earlier 2, म्हणजे पहिल्या दोन माहित असतील तर पुढच्या सगळ्या पॉलिनॉमियल्स काढता येतील. So this is one of the important recurrence relation from the examination point of view. Sometimes this is asked in examination. Okay, बऱ्याच वेळा हे विचारलं जाऊ शकतं. This is second property. Now third, number 3. Let's go for another. Now this time here differentiation with respect to x. H dash n of x is equal to twice n h n minus 1 of x. Looks very simple, but this is not that easy. So you have to go for differential of Hermite polynomial, first order differential h dash n of x, and show that right hand side of this is equal to twice n into h n minus 1 of x. So again proof. So let's start with this generating function, which is equal to g of xt is equal to e raised to twice xt minus t square is equal to summation over n equal to 0 to infinity. It is h n of x into t raised to n upon n factorial. Now we have to differentiate the given generating function with respect to x. Earlier मागच्या केसमध्ये आपण t ने differentiate केलं. This time you have to differentiate with respect to x. So differentiating g of xt with respect to small x, variable x. So again the differential here differentiating this, I'll get differential of this is simply twice t into e raised to twice xt minus t square. Differential with respect to x is only of this term in the index, so twice t comes out, t square will be 0, and differential of this e raised to twice xt into minus t square will remain as it is equal to, now summation over n equal to 0 to infinity, here h dash n of x, differential with respect to x, into t raised to n upon n factorial. So again replace this from our equation, or this recurrence, this is what generating function. So here we can e raised to twice xt minus t square can be written as summation over n equal to 0 to infinity h n of x into t raised to n upon n factorial. So replace this. Therefore next term is twice t summation n equal to 0 to infinity h n of x into t raised to n upon n factorial is equal to summation over n equal to 0 to infinity, here h dash n of x into t raised to n upon n factorial. Now take that t inside this summation bracket, summation, then you will get this to be equal to twice summation over n equal to 0 to infinity, then this h n of x into t raised to n plus 1, this t comes inside, divide by n factorial is equal to summation over n equal to 0 to infinity. Now this t h dash n of x into t raised to n upon n factorial. So here we have n plus 1. To make this t power t raised to n, what we have to do, on the left hand side replace n by n minus 1. Therefore I'll get here to be twice summation over n equal to 0 to infinity, it is h n minus 1 of x into t raised to n upon n minus 1 factorial is equal to summation over n equal to 0 to infinity h dash n of x into t raised to n upon n factorial. So compare the coefficients of t raised to n on both sides. So comparing coefficients comparing coefficients of t raised to n on both sides, simple as compared to earlier. On both sides we'll get, I'll get this left hand side is twice h n minus 1 of x divided by n minus 1 factorial, and one more thing is there. What is that? We have to add something there. Okay, yes, we will do that. We'll do that. Is equal to right hand side is simply h dash n of x divided by n factorial. I have to make n factorial both on the both side. Therefore, multiply it by n, divide by n. So n minus 1 factorial into h n minus 1 of x is equal to h dash n of x divided by n factorial. So here n into n minus 1 factorial is n factorial. So this and this can be cancelled, and therefore one will get h dash n of x, first differential with respect to x is twice n times h n minus 1 of x, and this is the required result. Required result. Just check what we have been asked. आपल्याला काय विचारलं होतं पहा. Okay, we have to prove. See the statement. We have to show that h dash n of x is equal to twice n h n minus 1 of x. So exactly same thing I got here as shown by this. So this is the required proof here. Second proof, one more, fourth property of this Hermite function, and this is now this is related to its parity or symmetry. What is this? this is hn of x is equal to minus 1 raised to n hn of minus x. That means Hermite polynomials of x and minus x are connected by this, provided n is even. This minus 1 raised to e1 is now plus. So for example, h2 of x and h2 of minus x, that will have same sign. No sign will be there because n is equal to 2, therefore minus 1 raised to n is 2. But if I go for h3 of x and h3 of minus x, h3 of minus x, in that case n is equal to 3, so minus 1 raised to 3 is minus 1, and therefore h3 of x will not be same as h3 of minus x. Their sides or their symbols will be changed, and that will have odd parity. So even parity and odd parity concept can be understood from this. So again, proof will go a bit faster here. Consider gf, generating function. Again it is g of xt is equal to e raised to twice xp minus p square into, that is equal to summation over n equal to 0 to infinity hn of x into t raised to n upon n factorial. This is my given generating function. Now with we have to replace something with transformations. Replace x by minus x prime and small t by minus t prime. Let's see what will happen to this our equation. Then I'll write this to be g of minus x prime and minus t prime is equal to, this is e raised to 2 minus x prime into minus t prime minus t prime square is equal to summation over n equal to 0 to infinity. It is hn of minus x prime. So everywhere you have to replace x by minus x prime and t by minus t prime. So it is minus t prime square upon raised to n upon n factorial. I can further write this right hand side as summation over n equal to 0 to infinity minus 1 times raised to n, okay, here into hn of x, minus x prime, hn of minus x prime. Now this minus 1 has been taken outside here, so it is t prime raised to n divided by n factorial. Okay, and here again, since we have taken them to be a dummy variables, so we can write as x prime and t prime are dummy variables, replacing them by x and t, we will get e raised to twice xt minus t square is equal to summation over n equal to 0 to infinity. This time minus 1 raised to n remains as it is here, and this is hn of minus x, x prime has been replaced by x, and multiplied by t raised to n upon n factorial. And see here, this is the left hand side is nothing but summation over n equal to 0 to infinity. This is hn of x into t raised to n upon n factorial is equal to summation over n equal to 0 to infinity minus 1 raised to n hn of minus x into t raised to n upon n factorial. So here the summation sign n equal to 0 to infinity and t raised to n upon n factorial is common. So what remains is there in the bracket is, therefore hn of x is equal to minus 1 raised to n into hn of minus x. This is the required result. Or here we can write explicitly, here if n is even, okay, then hn of x is equal to, even means there is going to be 1 here, so hn of minus x. The polynomial has even parity, has even parity. If n is odd, then hn of x is equal to minus hn of minus x. The polynomial has odd parity. Odd parity. Okay, this is the last property, and the last statement I am supposed to give here is again orthogonality. So fifth property of this Hermite polynomial is orthogonality. Now what we have discussed yesterday regarding this orthogonality in case of legendary polynomial, same thing is applicable here too, but this orthogonality condition plays a very important role in case of quantum mechanics when we go for solving the simple harmonic oscillator, quantum mechanical simple harmonic oscillator. This orthogonality property plays a very vital and important role. So these things you will understand when you learn quantum mechanics, maybe in the next semester or in this current semester, wherever it is. Okay, so let's write the brief and then we'll finish. The Hermite polynomials. Hermite polynomials do not satisfy the orthogonality relation. Do not satisfy the orthogonality relation. Hermite polynomials do not satisfy the orthogonality relation. However, by constructing orthogonal set of functions, orthogonal set of the functions, another functions phi n of x with the help of transformation. I am just giving as it is written in the textbook, no need to discuss much more about this. But those who want some more explanation of this, what is orthogonality, why it is not valid, here we can go for some standard reference book like RFKN or anything else. For PG students I am talking, you can go for that. So this transformation used here is phi m of x to be obtained by taking product of e raised to minus x square upon 2 into your Hermite polynomial hn of x. So from h0x I can get phi 0x, from h1x I can get phi 1x, from h2x I can get phi 2x, and so on. So when this function is transformed in this way, then these functions phi nx are called okay, transformed Hermite function. Transform Hermite function and satisfy orthogonality. That is the condition given here in this case is minus infinity to plus infinity integral of phi m of x into phi n of x into dx is equal to 0 when n and m are not same. Okay, so more about this. Now PG students, okay, those who are in MSc, they should go for this derivation from any standard reference book, to any book, Mathur or RFKN or anything else, but you have to complete this particular proof, because in examination in PG this proof is generally asked. बऱ्याच वेळा हे proof Hermite polynomialची orthogonality दाखवा. So this type of would be generally asked. So TY students need not worry about this, but the MSc students should go for this. And I think in our textbook this problem has been given in as a solution, okay, solved problem. Yes, this is given here. I think it is solved somewhere. आपल्या याच्यामध्ये सॉल्व केलेला प्रॉब्लेम आहे. There are 2-3 problems are there. I am giving this as an exercise later on for this PG students. For UG student that is not needed. So here we have finished this second special function, that is the Hermite function, as compared to first earlier, that is legendary special function or legendary polynomial. The derivation, the properties, the orthogonality etc. of Hermite function is much easier as compared to earlier case. So second function we have stopped here. Now in the next lecture we are going to start with this another third, that is the Bessel function of the first kind. Now how to derive this function, what is its Rodriguez formula, what is the recurrence relation for that, what are their properties, what are its applications etc. That all this, and which is its generating function too. These things we will discuss in the next lecture whenever we are going to meet there. Okay, so thank you for patience listening. All you have there. Now don't leave, let me stop this.